Hi, everybody. Welcome to this talk on the impact of very short-lived fluorine compounds, and we'll have a little bit about greenhouse gases on trends in stratospheric ozone. We greatly appreciate this fantastic author team. The motivation for this work is the slower than expected, in quotes, recovery of mid-latitude extrapolar total column ozone. There have been many papers on this topic. What we're going to do today is quantify the role that VSL, or very short-lived organic fluorine compounds, may be playing on the slower than expected recovery, looking at data from ACE, from ground-based FTSs, the PhD work of Maxime Brignon, and Atmos, as well as ground-based and aircraft measurements of organics. We're going to be using a multiple linear regression model to quantify total column ozone. The green is the NASA SPUV retrieval of total column ozone as a function of time, monthly time series. And the black is the result of a multiple linear regression model constrained by EESC, solar irradiance, aerosols in the strat, etc. Now, this specific EESC is found using the Newman fractional release factors for 3-year-old air. And we have this shortfall between the model and the data. The model's predicting a faster recovery. And this similar, many analyses are showing ozone's not coming back as we had expected. There's a lot of work being done on dynamics. Our work actually doesn't support the conclusions of some of those studies. We are in the VSL camp, and we're going to first look at the impact of the fractional release factors. So if I switch to the angle FRS, and I take your attention to these numbers up here, the reduced chi-squared over the last 10 years or 11 years, it goes from 3 to 1.9. So a physicist would say it gets meaningfully better, but we still have a normalized mean bias over the last 10 years where the model is about 1.3 DOPS units. This is the anomaly, the relative change of ozone, the change in ozone relative to the long-term mean. So we're about 1.3 DOPS units high. If we put VSL into the model, we're now really good reduced chi-squared. We're still a bit high, so we're not doing a perfect fit of the data, but we're certainly close to the data. And we start talking about, hey, I wonder what else is going on here. These are curves of EESC that underlie what I showed in the prior slides out to 2020 and out to the end of the century, computed using the Newman fractional release factors. There's the word Newman, for no VSLs and 3 approaches for VSLs. VSLs from the ground-based data, and then just taking the data and keeping VSL constant after 2020. About the same shape, because it's being held constant, as no VSLs. Now, Hassani et al. Published a 3.8 ppt per year rise in VSLs. If we apply that to the ground-based record, oh boy, now we have a different shape. And if we apply the larger fit of 6.1 ppt that my group gets from the aircraft data, then we get an even, sorry about that, an even faster or slower decline in EESC. We also do include VSL bromine. 30 is 60 times 50, 6 is the alpha, 300 is 60 times 5. I'm speaking too fast, I apologize. VSL bromine doesn't matter in terms of this analysis because it just lifts the whole EESC up. What does matter is what we're doing for VSL chlorine, because here I switch to the angle FRS. There's about a 2-year shift in the peak of when chlorine peaked. That's important, but long term, out towards the end of the century, there's little difference between Newman or Engel. The importance here is what's VSL doing? And if it keeps rising, we're going to have a slower than expected decline in chlorine, which obviously is very important. Okay, so let's take a closer look at the VSL chlorine species. This is dichloromethane. The black line is the annual mean record from global annual mean from NOAA A-gauge, NOAA network and A-gauge combined by Lee Hugh, thank you Lee. And the points are measurements from HORS samplers from aircraft campaigns in the tropopause transition layer from various regions. The work of Elliott Atlas and others and a few other groups. Okay, the data are just a straight comparison here. And so you see similar trends, maybe a slightly bigger trend in the aircraft data. This is in the air entering the stratosphere, but of course, who knows if this is representative of the global strat or the global entry. Okay, a different gas, methylchloride. Gotta see where the 3 is. So this is not methylchloride, it's chloroform. My bad. This is chloroform. Where's the 3? Okay, we got it. And that has a very similar shape between the aircraft data and the ground-based data. Now, we have scaled the ground-based data by 0.73 just to see how the curves compare in this manner. This could be tropospheric loss of this gas, methylchloroform, but reaching the lowermost strat. It has a lifetime similar to dichloromethane, so we shouldn't expect we would scale one without the other, but it is what it is. This is just visual. Okay, this is, I'm going to call PCE for short, from the aircraft data and the ground-based data, both showing a decline. Now, this gas has a shorter lifetime, so we do expect there to be more tropospheric loss of PCE. And so we're scaling by 0.3 here, just so you can visually see how the data compare. And then last, and actually least, because it makes the smallest contribution, is dichloroethane. Here we only have aircraft data going up, coming down, piecewise lower print. Okay, this line here is just from Lee Hugh, except for dichloroethane, we use that piecewise linear fitting. But now we're applying total chlorine. The other points here, the data points, are from the various aircraft campaigns. And if we fit the aircraft data, we have a more rapid rise than we infer either from the ground-based data or Hassani looked at part of this time period from upper stratospheric measurements from this. Anyway, the literal interpretation of the ground-based data, of the aircraft data, is a 6.1 part per trillion rise in fluorine from unregulated gases. Gases are not regulated by Montreal Protocol. They're anthropogenic. They're rising over time. This is pretty alarming. This is the chlorine component of EESC, just the chlorine component found using the Newman fractional release factors with no VSLs, VSL from the air, VSL from the ground. And the VSL from the air and VSL from the ground are just kind of literal interpretations of the data, which covers most of this time period. This time period. This is the time period, as you'll soon see, over which we have least observations. And I'm showing this slope of change between 2004 and 2010 for 3 cases. Now, if I go to angle, notice how these slope numbers hardly change. Again, between 2004 and 2020, the importance of the FRFs is a little bit over-exaggerated in a lot of people's minds. What's most important, in our opinion, is the contribution or lack thereof of VSLs to chlorine in the stratosphere. Chlorine in the stratosphere. Let's have a look at that. The black line with gray is an estimate of chlorine in 3-year-old air using this great method of Arlen Andrews et al., now 20 years old. Hey, Arlen, 20 years ago, using N2O to get 3-year-old air. And the data that we're using are the PhD work of one of our co-authors, Maxime Vignon. And so we try to nail 3-year-old air. We have a completely independent measurement from space, from ACE. We apply the same technique with this tiny correction here for unmeasured species. Okay, boy, neither ACE or Young-Frick is showing much of a change over time, and here's no Atlas paint. Now, the blue and red are estimates of the chlorine component to EESC without VSLs. And when we put VSLs in from the ground, we actually move away from the data. So you'll say, hey, Salawitch, what's up? This isn't particularly good news. And I'll say, yeah, but how about this? This is the fluorine contribution of 3-year-old air, which we can calculate from the Newman et al. Paper and the Engel et al. Paper using their methodology applied to just fluorine. It's fluorine, it's bookkeeping. So that's higher than the fluorine that we infer should be there for 3-year-old air from both Young-for-Yuck and FT and ACE. And so this is just telling us that we need to basically refine what we're doing to actually specify 3-year-old air. Okay. The most important part of this research, is comparison of the slopes. So I'm doing the average between using Newman and Engel. If we have no VSLs, chlorine should have been going down by 9.5 ppt per year. Young-for-Yuck and ACE say it ain't going down that much. It's going down much slower. If we put the VSL ground and grind out the numbers, we have an expected decline of about 6 parts per trillion per year, larger again than what's seen by Young-for-Yuck and ACE FDS. Now we have an independent view from Young-for-Yuck and ACE FDS that this rapidly rising VSL that we infer from the air may actually be what's going on in the strat. Because look, this number, 4 parts per trillion per year, is within agreement with and uncertainty with Young-for-Yuck. Now ACE is still pretty flat here, upper limit of whatever this is, 2 point something parts per trillion per year. Message here is that chlorine ain't going down in the strat at latitude 3-year-old air as much as we had expected it would. And that is the conclusion of the first part of the talk. I'm not going to read all these words here. Basically, the observed behavior of chlorine, inorganic chlorine in mid-latitude stress was broadly consistent with VSLs being important. We're going to know a lot more once the data from the NASA GCOTS campaign, which I'm very pleased to be part of the science team. Once these data are analyzed, we just had the first deployment this past summer. We ain't talking about it yet. Now we're going to talk about trends in ozone. We've seen this plot before. Just to remind you, our model has a more rapid rise in ozone than we observed from the SPV time series. We put an angle with VSL chloride and we come closer. Our normalized mean bias is now a pretty good number here, and we have a good reduced chi-squared, but we're still above the data. Let's look out in time. And this is where it becomes incredibly important. If I take the Newman fractional release factors literally, I actually expect that we should be halfway back between where we started in 1980 and the most depletion we got, right here. Now this is just the decline in ozone due to ESC. We have a separate Pinatubo here and solar here. So we should be at the halfway pole, halfway back. Last time I checked, 2021 was now. Should be halfway back. Go to Engel, we're 7 years delayed. Now, those who know me know I'm not particularly patient, but 7 years, well, the Engel fractional release factors are a more sophisticated approach, and maybe that's the better approach to use. So maybe we have to wait 7 years to get this very important halfway point. Sorry, my slides are slipping on me. Too much coffee today. Okay, now let's put VSLs in. Well, if I use VSLs from the ground-based data and I just keep them constant over time, I go from 2028 to 2036. That's 15 years. 2036, let's do the math. I'll be retired by then. And that's no rise in VSLs. Put a rise in 3.8 ppt per year. We're talking at 2040 to get to the dang on halfway point that the Newman FRFs without VSL chlorine says we should be at now. And if 6.1 is true, we have to go to 2046 for that halfway point. Okay. Ozone is also affected by greenhouse gases as well as ODSs, figure 23 from the Q&As. Our next step in this work is to incorporate the importance of greenhouse gases on total column ozone, because everything I'd shown you before, those curves were just the effect of ODSs. So we're working with Eric on this. Here are the conclusions to this talk, which is just about over. It's going to be very important to continue to measure VSL species, most of which are anthropogenic and are not regulated by the Montreal Protocol. Here are my references. Thank you very much. Have a good AGU.